Alright, in section 4.2 we talk about two main ideas. The first one is called Rawls' theorem, named after a mathematician named Rawls. And then there's the mean value theorem, which is even more important than Rawls' theorem. Alright, so to arrive at the mean value theorem, we first have to understand Rawls' theorem. Rawls' theorem says let f be a function, let f be continuous on the closed interval, then also let f be differentiable on the open interval, and also the endpoints have to be, f of each endpoint have to be equal. Then the theorem says that there's a number c in between a and b, or contained in a and b, such that f prime of c equals 0. And so if you look at some typical functions that satisfy these hypotheses, we can look at a constant function. Looks like a quadratic. You got a cubic there and another quadratic. But here you've got a and b endpoints. The f of a equals f of b, and there's many numbers c that where the slope is 0 of the tangent line. And the same thing here. These two, f of a equals f of b, and the slope of the tangent line is 0. So that's a value c that satisfies the theorem. And same thing here for these two different ones here and as well as here. Right? Now what does the mean value theorem say? The mean value theorem says if f is continuous on the closed interval and f is differentiable on the open interval, then there's the number c in that interval, open interval, such that f prime of c equals f of b minus f of a over b minus a. In other words, it's the slope formula, right? The first derivative at c equals the slope of the secant line, the line that goes through f of a and f of b. And we can call that secant line AB. Alright, we can see it's reasonable by interpreting it geometrically. Figures 3 and 4 show that points a, f of a, b, f of b on the graph of two differentiable functions. The slope of the secant line AB is given there, and that is also the same thing as equation 1 here. Instead of saying f prime of c, they just say m, so they are the same thing. And so here's what we're talking about. If you've got endpoints f of a, f of b, and you draw a line between them, we call that a secant line, a line that intersects our known function at least twice. What mean value theorem says is there's some number c such that the slope of the tangent line at c is the same as the slope of this line. And so if you've got one right there, you can draw your secant line AB, and you can find two separate points where c f prime of c equals the same slope as secant line AB. Alright. Now they ask you to illustrate the mean value theorem with a specific function, x cubed minus x, from a equals 0 to b equals 2. So we're looking at the function from 0 to 2. So there's a couple of things you have to do, step by step. First, show that f is continuous on 0, 2, and it is. It's a polynomial. 2, f is differentiable on 0, 2, the open interval, and it is. It's a polynomial. It's differentiable. And now, if we're going to find this, remember this is one of two ways you can show the mean value theorem. You can show it with this equation 2 here, or you can use equation 1. Alright, if you show it using equation 2, you have to know what f of 0, f of 2, f prime of c. Well, f of 2 is just plugging a 2 into the function, you get 6. F of 0, you get 0. And f prime of x, when you take the derivative, you get this, so f prime of c equals 3c squared minus 1. Alright, so now you plug in everything that you know. You plug in f of 2, f of 0, f prime of c, and b minus a. And here you get 6, 0, you get 3c squared minus 1, and there you get 2. And that gives you 6, that gives you 2. You can divide by 2 and you get 3 equals this. Add 1, divide by 3, and then take the square root. And when you take the square root, you get positive 2 over the square root of 3 and negative 2 over the square root of 3, but negative 2 square root of 3 is not contained in the interval 0, 2, so we don't consider that a answer. So this is the only number that satisfies the mean value theorem. Now if you did it the other way, using equation 1 with the slope formula idea, you'd say f prime of c equals what f prime of c equals, and you plug in all your different numbers here, and you get this reduces to 3, and so 3 equals the left-hand side. You add 1, divide by 3, take the square root, and you get the same answer. There's two other small points to mention. If f prime equals 0 for all x in an interval, then f is a constant. F is just a constant line, horizontal line on AB, and that makes sense because if the slope of the tangent equals 0 for every single value of x, that means that the tangents are all have slope 0, and thus the actual function has to be 0, or it has to be a horizontal line. Number 7, corollary, it says if f prime equals g prime for all x in this interval, then f subtract g is constant, meaning it equals a constant on AB. And that is f and g differ only by some constant c. And we'll learn more of that in later sections and later chapters. Now, there are several problems in our assignments that ask you to use Rawls' theorem and some that ask you to use the mean value theorem. So Rawls' theorem involves questions 1, 9, 11, 13, and the rest are mean value theorem. So let's look at the Rawls' theorem questions first. So remember what Rawls' theorem says. It says, first show it's continuous on the closed, differentiable on the open, that the endpoints f of each endpoint are equal. Then there's some number c such that f prime of c equals 0. Alright, so here they want you to verify Rawls' theorem with question 1 here. So this is continuous and differentiable. It's a nice smooth polynomial, so it is continuous on closed 0, 8 and differentiable on open 0, 8. And f of 0 equals 3 and f of 8 equals 3, so all three conditions are satisfied. So there must be some number c or several numbers c's that when you take f prime of each of them you get 0, meaning the slope of the tangent line is 0. And you can see at 1 and at 5 you get that. And so it does satisfy the Rawls' theorem. Number 9, they give you a polynomial and they give you an interval, and we know that it's continuous on that closed interval and it's differentiable on the open interval. The endpoints, when you plug them into the function, you get the same y value, so it satisfies Rawls' theorem, at least the hypothesis. And now there must be some number c such that f prime of c equals 0. Well, f prime of c equals the derivative, which is 4x minus 4 with a c in there instead of an x. And when we set that equal to 0 and we solve it, we get c equals 1. Since 1 is contained in the interval from minus 1 to 3, it satisfies the conclusion of Rawls' theorem, or RT. This is a composite of a polynomial, so it is continuous and differentiable. If you plug in your endpoints, you get the same y value, so the endpoints are equal. And if you take the first derivative and set it equal to 0 and solve it, you end up getting numbers that are either pi, 3 pi, 5 pi, 7 pi, and so on. But if we're only talking about from pi over 2 to 3 pi over 2, only pi satisfies that. It's the only answer that's in this interval. So pi satisfies Rawls' theorem. Okay, now 13. Again, you take the derivative and you get this guy. You plug in the endpoints and you get the same y value, so the endpoints are okay. If you set the first derivative equal to 0, it doesn't have a solution. Now, you might say that that might contradict Rawls' theorem, but it doesn't, since f prime of 0 does not exist. Right? F prime of 0 is not in the domain of f prime. And also, the function is not differentiable at 0. It's got a corner there. So since f is not differentiable, this does not contradict Rawls' theorem. Alright, so let's look at the questions that deal with mean value theorem. Question 3. This is a continuous and differentiable function on the closed interval and the open interval. So if we can follow the mean value theorem, we should be able to prove that the first derivative at some number c equals the slope, basically, of the endpoints. Right? And so we're talking about endpoints g of 8 and g of 0 and 8 and 0. When you take the derivative there, you get, when you simplify, you get 3 over 8. So g prime has to equal 3 over 8. Well, if you look at this graph, you can see right about where it's 2.2, that looks like it's about 3/8. And over here at 6.4, again, it looks like a slope of 3/8. So it satisfies the condition. Then they say, what about in the interval between 2 and 6? Well, that changes your slope here, because now you're taking g of 6 minus g of 2 instead of g of 8 minus g of 0. But you get a slope of minus 1/2, and the estimate is that your answer's slopes are at 3.7 and at 5.5, roughly. Those give you a slope of negative 1/2. Question 5. Does it satisfy the hypothesis of mean value theorem? Well, it's continuous on 0, 5, but it's not differentiable. Thus, it does not satisfy the mean value theorem. 7. Does it satisfy the mean value theorem? Well, it's continuous on 0, 5. It's differentiable on 0, 5. Thus, it satisfies the mean value theorem on 0, 5. So, a line passing through these the endpoints has a slope of 2/5. So, we should be able to find a tangent line that has that same slope. And when we do, we estimate its number for the x value is about 3.8. You look at 15, it says verify mean value theorem. So you've got a continuous function on a closed interval, you got differentiable function on the open interval. You take the first derivative and you find the slope of the endpoints is 1, and you take the first derivative, set it equal to that slope, and solve, and you get c equals 1. Now 1 is in the interval from 0 to 2, so that satisfies the mean value theorem. 17, ln of x is continuous on the interval. It's also differentiable. So when we take the slope of the endpoints, we get ln of 4 over 3. If we take the derivative, we get 1 over x, or 1 over c, and we set that equal to ln of 4 over 3. And we multiply both sides by c, or just flip both sides, reciprocal rule. You can flip both sides and they're still equal. And so c is approximately 2.16, which is contained in the interval 1, 4. 19, when you take the derivative, you get this guy. And we're talking about from 0 to 4, so we're going to take the slope of the endpoints and we get 1/2. We set our derivative equal to 1/2, but we plug in a c for x. And then we just solve it for c. I flipped both sides and got this. I divided by 2, I got that, and I squared both sides and I got 1. And it shows a graph of the secant line and the tangent line. They both have a value of, they both have the same slope of 1/2. And the value is c equals 1. And so 21 is the same idea. You're just taking the derivative, and then I use the other form of the equation. That's equation 2. And instead of doing the slope formula, it's just f of b minus f of a equals f prime of c times b minus a. It's just one slight diversion from the original problem. If you multiply both sides by b minus a, you get this. So it's the same as the slope formula, just slightly different written. So now if you're going to do that, you need to know what the endpoints are. You need to plug them in. Plug in a c for f prime and reduce it down. And you get that it doesn't contradict because the